Okay, so good morning. So this is the lecture 4. Let me just make them full screen. One moment. How do I do that? Like that. Yeah, so welcome to this semester we are looking at complex analysis 1. By the way, this was just a surprise for me. I didn't know I was giving this course. But anyway, now the course outline is somewhere there. I mean, in the Odell, some of you are saying that they don't understand it, but basically just look at the teaching, the content, okay? More or less, it talks about what complex numbers are, playing around with complex numbers, limits, and then eventually talk about functions and then analytic functions and then differentiability. That's more or less the content, okay, in Word. Yeah, so this 1, 2 weeks, well, most of the course will be done, supposed to be hybrid, but I'll do online because anyway, it's not been easy to get all of you together, to put you together and then you sit in a room. But anyway, this being online means that you need to, as you watch these lectures, you will need pen and paper to work. That's how we do mathematics, okay? So straight away I get into the course. So yeah, I've written week 1, week 2. Hopefully this screen is, let me just keep moving it up and down. But anyway, yeah. So I'm the course lecturer, and the course is MAT201, which is complex analysis 1, not square, okay? And today I believe is 29th, if I'm not wrong. All right. So let's dive in. So the first definition of the course is what you call what's a complex number? A complex number, we shall use Z to denote it, is a number of the form x plus iy, where x and y are real numbers, and I is the square root of -1, or I squared is -1, what we call the imaginary unit. This definition, we are calling definition 1.2, is more or less emphasizing on exactly what complex numbers are. But anyway, so one way of defining complex numbers is to think of them in algebraic form. That means it's an equation. Z is an equation of x plus iy. We've just said x and y are real numbers, and I is the square root of -1. Or we can think of Z, the complex number Z, in geometric form. The geometric form means that, remember what you used to call the XY plane or the Cartesian plane. And so we can think of Z as, well, I mean, defined by these two poles. You can call them X and Y are real numbers. So X axis, the horizontal axis, represents X, would be what you may call the real part. And the Y part corresponding to the complex part would be the imaginary axis, if you want me to call it. So number 3 says that the real part of a complex number is X, the horizontal axis, and the imaginary part of a complex number, which we denote by imaginary of Z, is Y. All right. So Z, this Z, has a real part and imaginary part. The real part is this. The imaginary part is what corresponds to the I, which is Y. All right. So like if I give you a complex number, Z equals 2x plus 3i, then 3 is the real part, and I don't know, I say 2 is the imaginary part, okay? And we'll look at examples as we continue. So we denote C, the set of complex numbers. We denote by C the complex numbers. That is, we write a complex number set C is all those numbers Z, such as Z can be expressed in this form, where the algebraic form Z equals x plus iy, where I is the square root of -1 or I squared is -1. And then something to note here is that the set of real numbers is a subset of the complex numbers. Earlier on in your life, you came across natural numbers, which we said they are a subset of integers, n, a subset of z. Z integers is a subset of rational numbers, which are fractions, a subset of real numbers. Real numbers, we think of them as the whole from -infinity to positive infinity. And so that would be the z-axis. So R, the set of real numbers, is a subset, a proper subset of the complex number set. A nice way to think of it is to say Z. C consists of Z, which has X, the real part, and the imaginary part. And so if you set Y, the imaginary part will be 0, then you just have X. So Z would be X. That would be only the real number set. Then, of course, it has an extra part, which is the imaginary part. All right, so now once we define what the set of complex numbers are, the next natural thing is to talk about what we call the operations. So two complex numbers, you can call them Z1, which has X1 plus IY1, and Z2, which is X2 plus IY2. We'll be saying that these two numbers are equal if X1 equals X2 and Y1 equals X2. Basically, the imaginary part, which is Y1, equals the imaginary part, which is Y2, and the real part, X1, equals the real part, which is X2. And so now next, here shift this down, is that Z, this complex number set up as 0 is a complex number, which means that the real part X and the imaginary part Y are equal to 0. All right. So now I think I was talking about that actually the set of complex numbers, you can now introduce operations. All right. And the four basic operations we do know, we learned in our earliest life in mathematics were addition, subtraction, multiplication, and division. So this division number 2 is almost like a theorem or proposition. I can just tell you a question I'll ask you. Now here, pay attention, and I say it slowly. I could ask you, show that the set of complex numbers C is a field. Show that the set of complex numbers is a field. Field like the one you play outside, but now this is just a field, okay, in terms of structure, all right? Like a set with operations, all right? So what that means is that for all complex numbers Z, addition, subtraction, multiplication, and division are possible, and they will be defined as follows. Now, as you know, these operations are binary, meaning what? That when you are adding, subtracting, multiplying, and dividing, you need two things that you are adding, two things you are subtracting from each other, two things you're multiplying, and two things you're dividing with each other, you know? So we will need, so we can pick two complex numbers, Z1 and Z2, that look like this. And then now we can say, well, how is addition defined here? So Z1 plus Z2, these two complex numbers can be added. How? The real part, which is X1, is added to the imaginary part, which is X2. No, sorry. X1, the real part of the first one, plus the real part of the second one, is X1 plus X2. And then the imaginary part of Z1 is this one. The imaginary part of Z2 is this one. So Z1 plus Z2 will be X1 plus X2 plus I into Y1 plus Y2. Full stop. Now, how about subtraction? Well, likewise, you subtract Z2 from Z1, that means Z1 minus Z2 equals, you subtract X2 from X1, so X1 minus X2 plus I into Y1 minus Y2. Full stop. That's as far as addition and subtraction are concerned. All right. Next is now multiplication of complex numbers. Now here you need to pay attention. So how do we multiply two numbers? Well, these are numbers, they're complex numbers. So it's a mix of real and imaginary. So you'll have Z1 times Z2 equals, so you write them adjacent to each other. So you'll have X1 plus IY1 times X2 plus IY2. How do you perform the multiplication? Well, you just take, I don't know whether you remember binomial expansion, but it's just X1, you multiply by the whole of this, and then IY1, you multiply by the whole of this, and then you bring them together. So this is how that works. So X1 times this guy will be X1, X2 plus I X1, Y2, all right, which is this one, plus IY1 times X2, IY1, X2, IY1, X2, or X2, IY1. And then IY1 times IY2 will be I squared Y1, Y2. But do you remember what, no, I don't know whether my mouse doesn't seem to want us to go backwards. But anyway, fine. So do you remember when you multiply I times I, you get I squared. But I squared is minus 1. So that's why you have this number here. This is I squared Y1, Y2, but I squared is minus 1. So you'll have the product of these two is X1, X2 minus Y1, Y2 plus, remember, this guy was multiplied by this guy. So you have I X2, Y1, and then you have this guy multiplied by this one is I X1, Y2, which is this. So the product of these two numbers is, the real part will be X1, X2 minus Y1, Y2. And the imaginary part will be X2, Y1 plus X2, I mean, XY1, Y2. All right, so you take a piece of paper and multiply this first guy by this plus this second guy multiplied by these two guys, and then you bring them together. The only thing I can just mention is that IY1 times IY2 is I squared Y1, Y2, but I squared is -1, so it becomes that. And then you group them together. All right, the I's, the ones with I and the ones without I. The ones without I correspond to the real part. The ones with I correspond to the imaginary part. All right. Good. So far, so good. Now, lastly, division. So you divide Z1 by Z2. So here, before we do the division, we shall define what we call a complex conjugate. All right. So we first define complex conjugate. So suppose if Z is a complex number, which is X plus I, Y, its complex conjugate, the complex conjugate of Z, denoted by bar Z, is this guy, but you negate the imaginary part. So it's just going to be X minus IY. All right. So for instance, if you had, I don't know, pay attention, 2 plus 3I, suppose Z equals 2 plus 3I, all right? 2 plus 3I, which is our Z. Then its complex conjugate will be bar Z, then you'll just have 2 minus 3I. That would be the complex conjugate, all right? And so now we can define the division of complex numbers. So how do we do that? Well, as we continue, please note the addition, subtraction, multiplication, whenever you multiply two complex numbers, you add or subtract, you get a complex number. What does that mean? That you always get a real part and an imaginary part, an I part, okay? So likewise here, when you're dividing these two numbers, this guy by this guy, you have to be able to get a real part and imaginary part. So how will that come about? And here again, I ask you to take a pen, a piece of paper and a pen and write it down. As you can see, I've just prepared notes for you. So, I mean, I don't need to write down anything, but you should. So perform the division here. So with Z1 divided by Z2 will be, you replace Z1, which is X1. All right, so let me just pick it, okay? Now, and I'll say it slowly so that at least you capture it. So in your reading this, you will have Z1 divided by Z2, which will now write Z1 is X1 plus IY1. Then you divide by X2 plus IY2. That's what you will write. So your fraction here, before you write all this, work out all this, here you have this guy over this guy. X1 plus IY1 over X2 plus IY2. All right? So you have something that looks like, well, I don't know, like that. I mean, this, but now with the corresponding numbers. And now you perform the complex conjugate for the denominator. You know what that means? Now, your fraction, which is X1 plus IY1 divided by X2 plus IY2. Now, you will multiply by the complex conjugate of the denominator. What's the denominator? This is the denominator, X plus IY2. So you have new fraction now, which is X1 plus IY1 over X2 plus IY2 will be equal to X1 plus IY1 over X2 plus IY2 times the complex conjugate of this guy, which is X2 minus IY2. So X2 minus IY2. Then what you multiply with, you divide by. So you also divide by the same complex conjugate. All right. So in other words, your fraction here now will be X1 plus IY1 over X2 plus IY2 times X2 minus IY2 divided by X2 minus IY2. Okay? And now here there's some multiplication for you to perform. What are you going to be multiplying? I don't know whether I'm able to write on the screen. Let me see whether this allows me. Enable, let's see one moment. I don't want to make the video very long, but let's see whether I can do that. I could. Would this allow me? Yes, it allows me. So now here you have a fraction. This is what we are saying. Here you have a fraction. You will be multiplying xy1, x1 plus y1 times, remember this is divided by, remember over here you have x2 plus I y2, okay? So what I've told you, so this is what you're dividing. Z1 over Z2 equals this. But you multiply by the complex conjugate of the denominator. So this will be times x2 minus I y2 divided by the same thing. X2 minus I y2. All right? So that's what you have. So Z1 over Z2 now reduces to this. And now you have two things you need to multiply. X1 plus IY1 times X2 minus IY2. So if you perform the multiplication here, what will you get? You'll get X1 plus X2. So this will be equal to, I hope this will not take too long, but anyway, this X1, X2, so this times this minus X1, you multiply by this IY2. So it will be I X1 Y2, all right? So you multiply x1 times these two guys, you get x1, x2 minus I x1, y2. Next, you take I, y1, you multiply by this guy, you get plus I can write y1, x2 or x2, y1. So I'll write x2, y1. So far, so good? Yes, I believe. So this guy times this guy is I y1 x2 or I x2 y1. Then lastly, IY1 times IY2, what does it give you? Well, it gives you minus, I'll just write it down, okay? Minus I times I is I squared, right? Then Y1, Y2. Y1, Y2. And so, ladies and gentlemen, guess what? That's all for the numerator. So you need to do something about it. But anyway, now, in the denominator, what do you have? Well, you have something similar, only that the two guys are similar. In other words, you have x2 times x2 iy2. So this will be x2 squared, isn't it? And then you'll have x2 times this guy will be, now I hope this doesn't take space for us. So let me just, I'll write it far away so I don't cover this guy. It doesn't matter, it's okay. So x2 times x2 minus iy2 is x2, x2 which is x2 squared. Then x2 times iy2 will give you minus I x2 y2. Then lastly, you have I y2 times this guy. It will be plus I x2 y2. This is x y2. So I y2 times x2 is I y2 x2 or x2 y2. And lastly, I y2 times minus I y2 it gives you plus, or rather minus, I squared x2, no, y, sorry. This is y2 squared. Just check whether I've written this correct. It is. So repeat, x2 plus iy2 times x2 minus iy2 is x2 times x2 is x2 squared. Then x2 times minus iy2 is minus I x2 y2. Then I y2 times x2 is minus I x2 y2 minus I squared y2. Now let's simplify this. So here, numerator, you have x1, x2. This is minus I squared y1, y2. So minus, so I squared is minus 1. So it's minus 1, so it's plus. So this becomes x1, x2 plus y1, y2, which is this one. x2, x1, x1, x2 plus y1, y2. All right, that's done. And then this one here, you have minus I x1, y2 plus I x2, y1. You pull out the I, you rearrange a positive one. You'll have x2, y1, which is this, minus x1, y2, which is this. The I is pulled out. So numerator is gone. It's good. Then denominator, you have x2 squared, which is this. And then now here you have minus x2, y2 plus x2, y2. That goes away. So this will cancel out. All right. It will be 0. And then minus I squared, y2 squared. Remember, I squared is minus 1. So minus 1 is plus 1. So it becomes plus y2 squared. And so really, z1 divided by z2 becomes x1. Now remove this thing here. So it becomes x1 plus x1, x2 plus y1, y2 plus I into brackets x2, y1 minus x1, y2 divided by x2 squared plus y2 squared. Now here, the way I wrote the answer, actually split it into two. So you have the real part has no I, and the imaginary part, the one that with I. That's why I wrote the answer like this. And why? Because I've told you, as far as definition of what you call what do you call them? The operations is concerned, when we add two complex numbers, when we subtract two complex numbers, when we multiply two complex numbers, and when we divide two complex numbers, we should get a complex number. What is a complex number? It must have a real part, it must have an imaginary part. So the real part, imaginary part. And so, ladies and gentlemen, that is what we call operations, the four basic operations on the set of complex numbers. And now this is the one I told you that earlier on, the first major result that you guys can be asked to perform is show that the set of complex numbers C is a field. So let me even write it here for you. Show, so this is the first exercise I'll ask you to be able to perform. So show that, and I'm not really very good at this, but anyway, show that C is a field. Oh, that's supposed to be A, but anyway, let me just write for you. The field is like this. F-I-E is supposed to be E. L-D. Full stop. Show that C, the set of complex numbers, is a field. I give you 10 marks or 10 points for this. So you should be able to define, you pick two complex numbers, Z1, Z2, and show addition can be done. This is what we did. Show subtraction can be done. This is what we did. Show multiplication can be done. This is what we've done. And show division. Z1 divided by Z2 gives me this kind of thing. So that is what all these stories I've given you, they are summarized here by saying that C is actually a field. A field in algebra, or I mean, in actually mathematics, in general, in any mathematical field you deal with, a field will be a set which you can perform the four basic operations, namely addition, subtraction, multiplication, and division. As far as the set of complex numbers is concerned, that's it. All right, so other properties that may be defined over for complex numbers, as we now continue our lecture, which I don't want to make it very big, would be, what you call commutative. Commutative just means that when you add two complex numbers, it doesn't matter the order you add them. So Z1 plus Z2 is Z2 plus Z1. How you would show that, you just pick Z1, which is this, plus Z2, which is this. And when you add, you will get Z1 equals, Z1 plus Z2 is X1 plus X2 plus I into Y1 plus Y2. Now, X1 plus X2, these are real numbers, the same as X2 plus X1. And Y1 plus Y2 is the same as Y2 plus Y1. And that proves for you commutative law, period. Now, the third one or fourth one is what you call associative law. Associative law just says that a order for any three does not matter. You can see we have three complex numbers, Z1, Z2, Z3. It doesn't matter the order you pick them. That's it. Likewise, we can also talk about commutativity and associativity for multiplication of two complex numbers. When you're multiplying two complex numbers, you remember our multiplication was done this way here. It won't matter if you write Z1 first or Z2 first. Z1 times Z2 or Z2 times Z1. It will give you the same thing. Please check that, okay? Check if now you put this one here and this one here. and multiply it, you get the same thing. And lastly, for associative for three complex numbers, when you're multiplying them, it won't matter the order you multiply them. Even that you can show or check. And lastly, what you call the distributive law. Now, distributive, now my slides are lying here, but anyway, I will correct them. They say we only have 3 slides, but there are many more. So distributive law just means that multiplication of a complex number over the sum of two complex numbers is distributive. That means that Z1 is multiplied over Z2, Z1 is multiplied with Z3, and then the two are added. So you have Z1 times Z2 plus Z3 is the same as Z1, Z2 plus Z1, Z3. That was fast. I am done there. All right. Okay. Let's go to the next slide. Now, these guys don't want to move. Oh, how do I do that? Okay, let me close this. All right. Okay. So now example here, given Z1, so this seems to be recurring. I don't know what I will do to remove it. Probably I can do that. Let me see whether I can do that. Is there a rubber here? How do you rub? Here it is. So we can rub this, yeah? Yeah, perfect. Awesome. All right, so far so good. Take your time to check this, but now we continue with our lecture. So end of annotation. Okay. Yeah, so given two complex numbers, Z1 is 2 plus 4i, and Z2 is minus 3 plus 8i. You are supposed to perform two operations. One is add the two. So Z1 plus Z2 will be 2 plus minus 3, will give you minus 1. And then 4i plus 8i will give you 12i. Done. Next, Z1 times Z2. So you multiply Z1 by Z2. So I just do the multiplication very fast. So you just have 2, you multiply by this guy, will give you minus 6 plus 16i, which is that. Then 4i, you multiply by this, will give you minus 12i minus, or rather plus, 32i squared. But I squared is negative, so this becomes minus 6 plus 16i minus 12i minus 32. So you bring the reals together. So minus 6 minus 32 is minus 38. And then 16i minus 12i is 4i. And that's it, ladies and gentlemen. Right, now we already defined the complex conjugate. So I just repeat the definition here more officially. So the complex conjugate Z of a complex number Z is just you negate the real part, the imaginary part. So x plus iy is complex conjugate denoted by Z is x plus x minus iy. And there's 4 properties or 5 properties or 6 properties of complex conjugate. So one is the complex conjugate of the sum of two complex numbers. That means you take the complex numbers, you add them first, and then now you find their complex conjugates. The same as first finding the complex conjugate and then add them together. For addition, for subtraction, it works the same way. Multiplication, likewise. Division, the same thing. So basically, complex conjugate will still satisfy the properties for C being a field. So it doesn't matter whether you take complex conjugate before or add, multiply, subtract, divide, period, right? Now, lastly, here you have, well, last two. The real part of Z is X, which is Z plus by Z. Well, let's just explain this very quickly. So the real part, look at this. Z equals X plus IY. By Z, the complex conjugate of Z is X minus IY. So if you take this guy, you add to this guy, what happens? You get Z plus by Z equals X plus X, which is 2X, and then my IY minus IY is 0. So it turns out that Z plus by Z is 2X. So you divide by 2, you get X is complex conjugate of Z plus Z. Then, and X we said is the real part of Z. Remember, the real part of this Z is X. The imaginary part of this Z is Y. Now, if you take subtraction, the difference, Z minus by Z is just X minus X is 0, and then you have IY minus IY is 2IY. So you have Z minus by Z equals twice IY. So what is Y? I mean, so now if you take so here the relation should be, let me just write it down here again. My slides are going to be very long. I hope it doesn't mess us up, but okay, fine, no worries. So it's just saying that Z plus by Z minus by Z equals, you're taking this plus this, you subtract. So x minus x is 0, so iy. So this gives you twice I y. So what is y? It will be the sum of the two, z minus by z divided by 2i. So here there should be an I, in other words. Okay, ladies and gentlemen. Okay. Hopefully it has agreed. Okay, so that's that. Next, we have now given two complex numbers. Now divide, all right, perform the division. So z divided by z. So it's just z1 over z2, and then you find 1 over z1. So here is the working for you. Again, I'm trying to hurry up, but so far so good. Now this we can remove, but I will not remove now yet. So z1 over z2, remember z1 is 2 minus 3i, z2 is 4 plus 6i. So remember what we did earlier on. So this now, you will write it like that, and then you multiply by the complex conjugate of the denominator, which is 4 plus 6i. So 2 minus 3i, this equals 2 minus 3i divided by 4 plus 6i times the complex conjugate of 4 plus 6i. Complex conjugate of 4 plus 6i is 4 minus 6i. So whatever you multiply with, you also divide by the same thing. So here now it turns out you have two complex numbers, two sets of complex numbers to multiply. So the numerator, this guy times this guy. Denominator, you have this guy this guy times his complex conjugate. So let's perform the multiplication here very fast. So 2 multiplied by this guy will give you 2 times 4 is 8. Then 2 times minus 6i is minus 12i. Then 3i times 4 is minus 12i. Then minus 3i times minus 6i is plus 18i squared. That's as far as the numerator is concerned, that's it. The denominator, what do you have? 4 plus 6i into 4 minus 6i. So it's 4 times 4, 16. Then you have 6i, 4 times 4 is 16. Then 4 times this guy here, you get minus 24i. Then 6i times 4 is plus 24i. So minus 6 minus 24i minus plus 24i goes away. So you remain with 4 times 4, which is 16, and then 6i times minus 6i is minus 36i squared. I squared is minus 1, so it becomes plus 36. If that's not clear, I will explain, but that's it, okay? And then now you open up, so you end up with the reals. So this I squared is minus 1, so it's 8. Minus 18 is minus 10. And then 12i minus 12i is minus 24i. Then 16 plus 16 is 52. This is the answer, which you can split into real part, which is minus 10 over 52, which is minus 5 over 26. And then minus 24 over 52i is the same as 6 over 26i, which you can simplify further if you like by 2, but that's it. Okay, now I'm thinking this lecture should be over, but anyway, let's just finish up. Let's remove this because I think the rubber will do that on us. All right. Okay, fine. Now, last one is the divide 1. 1 is a complex number, by the way, by z1. So it will be 1 over 2 minus 3i, which you repeat the process again. So what do? This will be 1 over 2 minus 3i times the complex conjugate of 2 minus 3i. The complex conjugate of 2 minus 3i is 2 plus 3i. So you will have 1 over 2, 1 divided by 2 minus 3i times 2 plus 3i divided by 2 plus 3i. And so what happens? Numerator will just be 1 times this guy is just this guy. Then denominator is 2 times 2 is 4, all right? And then here you have 2 times 3i is plus 6i, all right? Then minus 3i times 2 is minus 6i. And then you have minus 3i times plus 3i. It is minus 9i squared. So minus 9i squared, the I squared is minus 1, so it becomes plus 9. And then 6i minus 6i is 0, so you remain with 4 plus 9, which is 13. So you have 2 plus 3i over 13, which you can write in the real part, which is 2 over 13. The imaginary part is 3 over 13i. Good? Very good. All right, now, ladies and gentlemen, I think I want to wind up, but anyway, let's just define a few more things. I think this lecture can go on and on. So what we call a modulus, or the absolute value of a complex number, which we denote by this. Suppose Z is a complex number, then its modulus denoted by this will be given by the square root of the real part squared plus the imaginary part squared, square root, which is also the same as the square root of the modulus times the complex number. Okay, this you can check. All right. Then there's a proposition. This we will prove, but this is the first. Well, I gave you two homeworks. One is show that C is a field. Show that the set of complex numbers is a field. The second homework I'll give you, which you will submit, by the way, next week, is this. This is going to trick you, but I will help you, okay? So this is it. Let me just, what do you call, write here. Where is the pen? So this is homework. You research on it and do it. It's not very complicated, okay? Well, even this class is almost homework because I'm doing it from my house, all right? Anyway, so what is this saying? Well, the homework is just saying that you guys need to prove, given two complex numbers, Z1, Z2, then the modulus of Z1 plus Z2 is less or equal to the sum of the individual moduli. This is called a triangular inequality, which we may have done in real analysis 1 or 2. Now we extend it to the set of complex numbers, it actually works. So please check that, okay? So you have the second homework. Then you have, given a complex number Z is 2 minus 3i, find its modulus. So modulus, we said, is just the sum of the real part square, the imaginary part square, then you find the square root. So the real part squared is 2 squared, the imaginary part squared is minus 3 squared. So that's 4 plus 9, which is 13, then you find the square root. Good? Very good. All right, so here you have questions for you to answer. Let me see. Again, I'm trying to make this lecture short, but it looks like it's pretty long. Anyway, so what is it I'm asking you to do? Well, let's see, what time is it now? Ooh, time is gone. So express a given complex number Z equals x plus iy. I mean, express these numbers that are given in the form of x plus iy. So the number you're given is I power 8. So I power 8, this is pretty easy because it's just I squared, 4 powers, 4 copies of I squared. But I squared is minus 1, so just minus 1 raised to power 4, which is 1. So this is in this form because now the real part is x is 1 and y is 0. Finish? Yes. Now look at example number. This one, I think you check there and work it out. I will not look at it now. I mean, I'll say you have it in the notes. More examples. Express the given complex numbers as z equals x plus iy. So this one, again, please work it out. The solution is given. I'm not going to bother. Now the second week, now I will end the lecture here so that the next lecture, which I will share with you a video, will start from here. Okay? Polar and rectangular form. So far you have done 2 questions which you guys can answer. So I believe if we end now the video there, we will be good people, all right? So what are we doing? Stop.